Hi everyone, and welcome to this our last video in chapter 19, and this is going to be on sensing devices. What do we mean by this? Well, some electrical components may be used to sense environmental changes, right? I'm going to introduce some of these devices because we're going to talk about them in more detail, or rather their application, in future chapters. So think of this as a bit of an information dump kind of thing. So it's just more introduction to these different types of sensing devices, so you understand the general principles of operation. So the first one I want to introduce you to is something called an LDR, which is a light dependent resistor. So it's a resistor, and as the name implies, it's dependent on the light that's incident upon it. It is also sometimes called a photoresistor. It's passive. It's not really acting by itself, but the resistance of the LDR is going to decrease as the light intensity or luminosity increases. In other words, it exhibits photoconductivity. So you can have a photoresistor in light-sensitive detector circuits, or in light-activated or dark-activated switching circuits. In the dark, the photoresistor can have a resistance as high as several mega ohms, and in the light, you can have a few hundred ohms of resistance. In essence, if incident light on a photoresistor exceeds a certain frequency, the photons are absorbed by the semiconductor, and they give bound electrons enough energy to jump into the conduction band. Basically, generates free electrons. So when you have resulting free electrons, they conduct electricity, and that essentially then lowers the resistance. Another interesting thing about photoresistors is that they exhibit a little bit of lag, a little bit of latency between exposure to light and the resulting decrease in resistance, which can be about on the order of a few milliseconds. So the lag time when you're going from lit environment to dark environment is even greater. It can be as much as 1 second. And that property makes them unsuitable for sensing rapidly flashing lights. So typically what we find is we have inexpensive cells made of cadmium sulfide in many consumer items like, light meters and cameras, or clock radios, or alarm devices, night lights, street lamps, solar street lamps, outdoor clocks, or road studs that are solar ones. So those are some examples of applications of light-dependent resistors. The symbol for an LDR, or a photoresistor, looks like this. It basically, looks like a circle like this. Sometimes you have the resistor can sometimes be drawn like this, right? So you might see something that looks like this, and you're going to see two arrows on it which indicate the light that's being incident on it. So that is what a photoresistor would look like. Now, if you recall in the same chapter in an earlier video, we were talking about thermistors. So that a thermistor is a type of resistor whose resistance is strongly dependent on temperature, more so than standard resistors. So that is an example of another external stimulus, not light, but temperature, that can change the property of a resistor. So let's take a look at that guy a little bit more. So this is what the symbol for a thermistor would look like. You can have thermistors whose resistance increases with temperature, and those whose resistance decreases with temperature. So we have what we call negative temperature coefficient thermistors, where the resistance comes down as temperature goes up. So those are what we are going to cover in this course. I won't be covering positive temperature coefficient resistors here. So what I want you to understand, though, mainly for this is what does it look like? Like the profile of resistance versus temperature. So you might have temperature, going from, oh gosh, let's say minus 150 degrees. This is going to be in Celsius, going out to, let's say, a couple hundred degrees Celsius. So 0 is somewhere in the middle here. Obviously, I'm not drawing to scale, so please forgive me. And resistance will actually show in a logarithmic scale. So let's say you have like a mega ohm here, right? So this is going to be ohms. So this is going to be 1 mega ohm there. And down here, I'm going to say, oh gosh, let's say 10 ohms. 10 ohms to a million ohms, right? And then somewhere in the middle, I guess, we have like 10,000 ohms here and 1,000 ohms there, right? So the thermistor might actually give you a relationship that looks a little bit like this, something like this. So how does this work? Well, basically, you have free electrons bumped up by thermal agitation. So you've increased the temperature, so more free electrons are being released. And as a result of that, you tend to use NTC thermistors as temperature sensor type devices or current limiting type devices. So when we look at this, you'll see one thing. You'll notice it right away. This is a pretty steep curve. You're going down from a million ohms down to a few thousand ohms or a few hundred ohms over the course of a span of 350 or maybe 400 degrees of Celsius. So that's a very steep curve, isn't it? It's a very steep resistance temperature slope. So because you have a steep slope, that implies this has a high temperature sensitivity. But range is not that wide. So that's the shortcoming here. In terms of how you measure this, the temperature sensitivity of a NTC sensor is usually expressed as a percentage change. So you don't say how many ohms have changed, but you just say percentage change per degrees Celsius. So depending on the material used or the specifics of the production process, typical values are going to range, minus 3% per Celsius or 6% per Celsius, in that kind of range. So that's a typical number. So look at this this is very responsive. It's actually, turns out these are usually very small and they're relatively cheap to operate. So that's the advantage of the negative temperature coefficient thermistors. So there's another one that we can look at. So you've now looked at stimulus in the form of light. You look at stimulus in the form of heat. What about stimulus in the form of a mechanical strain, right? Like something you're pushing or pulling on something. So do we have a device that we could measure, in the same sense of using resistance as a parameter? Absolutely, we can. So if we go back and look at earlier videos in chapter 19, you're going to remember this equation, that resistance is equal to resistivity times L, the length of the wire, divided by the cross-sectional area of that wire or that component or whatever it is. So what does that tell you? It means that the longer something is, the more resistance it's going to have, and the larger the cross-section area something has, the less resistance it's going to have. So we can use this to understand how much strain is being applied on an object. So what we have is something called a strain gauge. It's a device used to measure strain on an object through changes in resistance. So how does this work? So let's take a look at what the structure of this thing looks like. So typically, you have a winding pattern of some kind of etched metal wire on a flexible polyamide film. And typically, copper nickel alloys are commonly used materials. The zigzag pattern actually helps avoid overheating and changing the resistance that's being measured. But the way that this is going to work is, if you have an electrical conductor that's stretched within the limits of its elasticity, such that it doesn't break or permanently deform. So what happens to it? You have something that has a shape that looks like this, and you've stretched it, right? So if you stretch it, it may, I'm exaggerating this a little bit, but it might start looking a little bit like this if you stretch it, right? So you're applying some tensile strain on it, not compressive strain, but tensile strain. You've made it longer and you've reduced the cross-sectional area. What's going to happen here? Well, the equation right here in front of you is going to say that in this situation, resistance is going to go up in the case of a tensile strain, right? And if we have another case where this is the original shape of something and you've applied a compressive force on it and it ends up looking like this, well, now you've reduced the length and you have increased the cross-sectional area. Well, in this case, resistance is going to decrease if we follow the equation on the top left here. So this is an example of a compressive strain that's being applied. So this is essentially, like going to tell us whether or not, depending on the amount of stress that has been induced, it tells us how much electrical resistance has changed. So you measure the electrical resistance of this strain gauge, and then you can infer the amount of induced stress that can occur as a result of this. So really, you're using resistance as a way of measuring something else. So you use resistance to measure what light would look like. I beg your pardon, how much light is incident on a surface. You use resistance to measure what temperature there is in the system. And again, you've now used resistance to measure how much strain has been applied or stress has been applied to an object. There's one further thing that we can look at, and that is called the piezoelectric effect. So I'm not going to cover this in as much detail because we actually did cover this, if you recall, in chapter 14, the piezoelectric effect. So very briefly, piezoelectric means electricity caused by pressure. Piezo is the Greek word for squeeze or pressure. So the way I want you to visualize this. The way I want you to visualize this is to think of a material like quartz. So not every material is piezoelectric. So some materials are piezoelectric, such as quartz. You can have quartz coated with a conducting material like silver. When stress is applied, like when you try and squeeze this quartz material, the ions in the material are going to move from towards one of the conducting surface while moving away from another. So by squeezing or by causing some pressure onto something, you are generating electricity. You're generating a potential difference inside a system. So an example of this, the application of this that specifically I want to talk about in this video is what's called a contact microphone. Sometimes it's also called a piezo microphone. And what that does is it senses audio vibrations through contact with solid objects. So normally you have microphones in air, right? But contact microphones are almost completely insensitive to air vibrations, but they will transduce any sound that is born by a structure. As a reminder, the word transduce means when you convert energy from one form to another. Any device that can convert energy from one form to another is called a transducer. So in this case, the sound waves that are being born by a structure are going to get transduced into some kind of an electrical signal. So this thing is often used as an acoustic leakage probe, right? So you can, like anybody who's experimenting with sound, like some music artists, they might enjoy using this. You also use this to amplify sound from acoustic musical instruments, to sense drum hits, to trigger electronic samples, or to record sound in challenging environments such as underwater, under high pressure. So what we find is these guys are usually made up of ceramic round glued to some kind of metal like brass or some alloy metal disc. And the center of this disc is positively charged. So you might have a quartz disc, right? And around it, you might have another metal disc. So the center is going to be positively charged. The outer side is going to be negatively charged. So if when you apply pressure to it, right, it's going to, if you hook it up to some kind of a voltmeter, you might actually get a signal. If the disc is cracked or scorched, this thing is not going to function at full sensitivity. So just be aware of that. So this guy in here is what we call ceramic round, and let's call this alloy. So if you squeeze the metal on the outside, or rather the piezoelectric material on the outside, you're going to cause the ions to move in one direction and away from the other, away from the like charge. As a result of that, that generates voltage, and that's your piezoelectric transducer. So folks, that brings us to the end of this video as well. Hopefully you enjoyed it. We will see you in chapter 20. Thank you.